Imagine holding a grain of sand. Now picture that grain magnified 1,000,000 times. You still wouldn't see the tiny particles that make up its essence. These particles are atoms, the fundamental building blocks of everything around us. Despite their minuscule size, atoms hold the secrets to all matter in the universe. From ancient philosophers to modern-day physicists, understanding atoms has been a quest filled with discoveries that changed the world. Each breakthrough brought us closer to comprehending the complex tapestry of the universe. This essay will take you on a journey from ancient theories to modern atomic models, highlighting the pivotal contributions of key scientists along the way. Early thinkers speculated on what everything was made of. So, let's embark on this fascinating journey into the heart of matter. Atoms are the building blocks of matter. Everything you see, touch, and feel is made up of these tiny particles. They are the smallest units of chemical elements, retaining all the properties of the element they compose. The concept of atoms helps scientists explain the properties and behaviors of different materials. Without atoms, the world as we know it wouldn't exist. Atoms interact in various ways to form molecules, which in turn create the diverse substances we encounter daily. From the water we drink to the air we breathe, atoms are everywhere, orchestrating the dance of life. Understanding atoms also allows scientists to manipulate materials at a fundamental level. This manipulation has led to technological advancements that have transformed our lives. For instance, the development of semiconductors, which are crucial for modern electronics, relies on precise control over atomic arrangements. The study of atoms has thus paved the way for innovations that shape our present and future. By delving into the world of atoms, we gain insights into the fundamental principles that govern the universe. At the heart of every atom lies its nucleus, a dense center composed of protons and neutrons. Protons carry a positive charge, while neutrons are neutral, having no charge. Surrounding the nucleus are electrons, tiny particles with a negative charge. These electrons orbit the nucleus at various energy levels, creating a cloud of negative charge around the positively charged nucleus. The number of protons in the nucleus determines the element of the atom. For example, a hydrogen atom has 1 proton, while a carbon atom has 6. Neutrons provide stability to the nucleus. Without neutrons, the repulsive forces between positively charged protons would cause the nucleus to fly apart. Electrons play a key role in chemical reactions. They are involved in forming bonds between atoms, leading to the creation of molecules. The arrangement of electrons in an atom's outer shell determines its reactivity and the types of bonds it can form. Understanding the structure of atoms helps us comprehend the diversity of elements and their properties. The concept of atoms dates back to ancient Greece, around 400 BCE, with the philosopher Democritus. He proposed that everything in the universe was made up of tiny, indivisible particles called atomos, meaning uncuttable or indivisible. Democritus's ideas were based on logical reasoning rather than experimental evidence, but they laid the groundwork for future atomic theories.
Democritus believed that atoms were eternal, indestructible, and varied in shape and size. He suggested that the different properties of materials were due to the different shapes and arrangements of their atoms. For example, he thought that sweet substances had smooth atoms while bitter ones had sharp, jagged atoms.
Although these ideas were speculative, they represented a significant step towards understanding matter's fundamental nature. Unfortunately, Democritus's atomic theory was not widely accepted in his time. Despite the initial lack of acceptance, Democritus's vision of atoms as the building blocks of matter was a revolutionary idea. Section 5. Dalton and the birth of modern atomic theory. Centuries after Democritus, John Dalton revived the concept of atoms in the early 19th century.
Dalton's atomic theory, published in 1808, marked the beginning of modern atomic science. He proposed that all matter is composed of tiny, indivisible particles called atoms. Dalton's theory provided a scientific framework for understanding matter. He suggested that all atoms of a given element are identical. Compounds are formed by the combination of atoms in fixed ratios. Dalton's contributions laid the foundation for modern chemistry.
Section 6. Thomson's plum pudding model. In the late 19th century, the discovery of the electron by J.J. Thomson led to significant advancements in atomic theory.
Thomson's experiments with cathode rays revealed the existence of negatively charged particles, which he named electrons. This discovery challenged the notion that atoms were indivisible and forced scientists to reconsider the structure of the atom.
To explain his findings, Thomson proposed the plum pudding model of the atom in 1904. According to this model, the atom was composed of a positively charged pudding with negatively charged electrons embedded within it, like plums in a pudding.
This model suggested that the positive and negative charges were evenly distributed throughout the atom, maintaining overall electrical neutrality.
Thomson's plum pudding model was a significant step forward in understanding the atom's internal structure.
It introduced the idea that atoms were not indivisible, but contained smaller subatomic particles. However, the model had limitations, as it could not explain certain experimental observations, such as the scattering of alpha particles. Despite its shortcomings, Thomson's plum pudding model was an important milestone in atomic theory.
Section 7. Rutherford's revolutionary nuclear model. The limitations of Thomson's plum pudding model were addressed by Ernest Rutherford's groundbreaking experiments in the early 20th century.
Rutherford, along with his colleagues Hans Geiger and Ernest Marsden, conducted the famous gold foil experiment in 1909. They bombarded a thin sheet of gold foil with alpha particles and observed their scattering patterns. To their surprise, most alpha particles passed straight through the foil, while a few were deflected at large angles.
This unexpected result led Rutherford to propose a new model of the atom in 1911. He suggested that the atom consisted of a small, dense, positively charged nucleus at its center, surrounded by a cloud of negatively charged electrons.
This nuclear model explained the observed scattering of alpha particles, as most passed through the empty space around the nucleus, while a few were deflected by the concentrated positive charge. Rutherford's nuclear model revolutionized atomic theory. It introduced the concept of the nucleus, a central core containing protons and neutrons around which electrons orbited.
Section 8. Bohr's quantum leap in atomic theory. Building on Rutherford's nuclear model, Niels Bohr introduced a new atomic model in 1913 that incorporated principles of quantum theory.
Bohr's model addressed the limitations of Rutherford's model by explaining the stability of electron orbits and the emission of light by atoms. His work combined classical physics with quantum mechanics, leading to a deeper understanding of atomic structure.
Bohr proposed that electrons orbit the nucleus in specific energy levels or shells, each with a fixed energy. Electrons could transition between these levels by absorbing or emitting energy in discrete amounts, called quanta.
This idea explained the observed spectral lines of elements, which corresponded to the energy transitions of electrons. Bohr's model successfully explained the hydrogen atom's spectral lines, providing strong evidence for his theory. Despite this, Bohr's contributions were crucial in advancing atomic theory and laying the groundwork for the development of quantum mechanics.
Section 9. The evolution to modern atomic theory. The journey from Democritus's early ideas to Bohr's quantum model set the stage for the development of modern atomic theory.
Advances in quantum mechanics and experimental techniques have further refined our understanding of atoms. Today, the quantum mechanical model of the atom, based on the principles of wave-particle duality and probability, provides the most accurate description of atomic structure.
In the modern atomic model, electrons are described as wave functions, representing the probability of finding an electron in a particular region around the nucleus.
This model, known as the electron cloud or quantum mechanical model, accounts for the behavior of electrons in multi-electron atoms and explains a wide range of chemical and physical phenomena. Technological advancements, such as electron microscopy and spectroscopy, have allowed scientists to observe and manipulate atoms with unprecedented precision. The evolution of atomic theory reflects the ongoing quest for knowledge and the power of scientific inquiry.
Section 10. The impact of atomic understanding on science and life. Understanding atoms has profoundly impacted science and everyday life.
It forms the foundation of chemistry, physics, and materials science. leading to innovations shaping our world from new materials and drugs to advances in energy and electronics.
In medicine, atomic theory enabled MRI and PET scans, revolutionizing diagnostics and treatment.
It has also influenced our perspective on the universe, providing insights into the origins of